Welcome back to the deep dive, where we really dig into the amazing things that make up our world. Before we jump into today's topic, just think for a second about the hidden architecture all around us. This kind of silent, ordered dance of atoms that shapes, well, everything. If you enjoyed these explorations and want to help us do more, we'd love for you to join the All Sorts podcast community over on YouTube. Please like, share, and subscribe. It really helps us bring more of these hidden corners of the universe into the light. And definitely check out our back catalog for other deep dives and connect with us and other listeners on X, Instagram, and Threads. Share those aha moments.
Yeah, definitely. And today, we're diving deep into something really fundamental. Understanding crystal structures, how they form, what types there are. We've looked at some interesting stuff for this, articles on X-ray crystallography, bits from chapters on metals and ceramic structures, info on symmetry, or basically how it all fits together. Our goal, really, is to see how these tiny arrangements end up controlling the big picture properties of materials we use constantly.
Okay, let's get into it. Our mission, crystal clear, you might say.
Oh,
sorry,
nice one.
is to really grasp how atoms line themselves up to form solids. We'll look at the different structures, how they actually come together, and why it all matters. Why one material is strong and another's brittle. This should be pretty eye-opening, actually. It's your shortcut to understanding that hidden order in everyday stuff.
Right. So first things first, how do atoms even organize in solids? We need to talk about crystalline versus amorphous materials. Think about stacking oranges perfectly at the store, that perfect repeating pattern extending out. That's like a crystalline material. Atoms lined up in a very ordered, repeating way.
Okay, super organized.
Exactly. Now,
Yeah.
Picture just dumping those oranges in a bin. No real order, right? That's more like an amorphous material. The atoms are all jumbled up, no long-range pattern. And interestingly, this order, or lack of it, can affect things like transparency. Often, the non-crystalline amorphous forms are clear, while the crystalline ones might be opaque or sort of translucent.
Huh. So how do we even picture these tiny arrangements? I saw something about the atomic hard sphere model. Is that helpful?
Oh, yeah, that's a great starting point. It's a model, a simplification, of course.
Yeah.
It just treats atoms like tiny solid balls. It helps us visualize how these spheres might pack together. And building on that, we get the idea of a unit cell.
Unit cell.
Think of it like one pattern tile on a floor. That single tile, if you repeat it over and over, makes the whole floor pattern, right?
Yeah, makes sense.
The unit cell is the smallest chunk that has the whole pattern and symmetry of the entire crystal. The whole crystal is just that unit cell stacked repeatedly in 3D.
And I guess these tiles or unit cells aren't all the same shape or size.
Exactly right. The specific shape and size are defined by what we call lattice constants, or lattice parameters. These are just the lengths of the edges of the unit cell, like the length, width, and height of a box, and also the angles between those edges. Are they 90 degrees or something else?
Okay, so those define the basic box.
Pretty much. And those parameters determine the overall geometry. Now, there's also this concept called Bravais lattices. There are only 13 unique ways you can arrange points in 3D space so that every point looks exactly the same as every other point.
Only 14 ways. For all crystals?
Only 14 fundamental geometric arrangements, yeah. These are the frameworks. But a crystal structure isn't just the points. You take a basis, which could be one atom or a little group of atoms, and you place that basis identically at each point of one of these 14 Bravais lattices. That's what gives you the final crystal structure.
Okay, framework plus atoms equals structure.
Got it. So how do these atoms, especially in metals, actually stack up layer by layer? I read about stacking sequences, A, B, C.
Right, for many metals, especially the ones that pack tightly, you can think of it as stacking layers of atoms. Imagine arranging marbles flat on a table, packed close. When you put the next layer on, the marbles sit in the little dips or sites between the marbles in the first layer. Let's call the first layer's positions A sites. The second layer marbles will sit in, say, B sites.
Okay, A, then B. Now, if the third layer goes directly above the first layer back in the A sites, you get a repeating sequence. A, B, A, B, B.
Like a simple sandwich repeating.
Exactly. And that ABF stacking gives you what's called a hexagonal close-packed structure, or HCP.
Okay, ABAB is HCP. What about the other one, ABC?
Good memory. So what if that third layer doesn't go above the A sites or the B sites, but finds a new set of dips? We call those C sites. You get A, then B, then C. And it's only the fourth layer that lines up back over the A sites. So the sequence is ABC, ABC.
So a 3-layer repeat instead of 2.
Precisely. And that ABC, ABC stacking gives you the face-centered cubic structure, or FCC. It's worth noting, though, that the body-centered cubic structure, BCC, another really common one in metals, doesn't really stack in these nice, close-packed layers. Its arrangement is a bit different.
That's a great way to visualize it, the stacking.
Okay.
So now we have a feel for how they assemble. Let's talk about the specific types of structures. You mentioned FCC, BCC, and HCP are common in metals. Can we break those down?
Absolutely. These three are super important for understanding metals. Let's start with face-centered cubic, FCC. Imagine a cube. Put an atom on each of the 8 corners, then put another atom right in the middle of each of the 6 faces.
Okay, corners and faces.
Right. Now, if you pick any one atom, how many others is it directly touching? In FCC, it's 12. That's its coordination number, CN12. And we can also measure how efficiently these atoms fill the space. That's the atomic packing factor, or APF. For FCC, it's 0.74, or 74%.
74%. That sounds pretty packed.
It is. It's actually the maximum possible packing density you can get with spheres of the same size. Metals like aluminum, copper, gold, silver, nickel, lots of common ones are FCC. And that type packing is related to why they're often quite ductile, easy to shape.
12 neighbors, max packing efficiency. Sounds stable. Okay, what about body-centered cubic, BCC?
Okay, picture the cube again. Atoms at the 8 corners, just like before. But this time, instead of atoms on the faces, there's just one single atom right smack in the center of the cube's body.
Corners and one in the middle. Got it.
Yep. And in this setup, each corner atom touches that center atom. If you look at the central atom, it's touching the 8 corner atoms. So the coordination number here is 8.
Fewer neighbors than FCC.
Exactly. And the packing factor, the APF, is a bit lower too, about 0.68 or 68%. So it's a bit less tightly packed than FCC. Metals like chromium, tungsten, iron at room temperature, that's alpha iron, tantalum, molybdenum, they often take this BCC structure, and these tend to be quite strong materials.
Right, a bit more open, CN8. And the last one, hexagonal close-packed HCP. You said it was also efficiently packed like FCC.
That's correct. HCP also has that maximum packing factor of 0.74 and a coordination number of 12, just like FCC. Its unit cell isn't a simple cube, though. It's based on a hexagonal prism. You have atoms at the corners of the top and bottom hexagons, one atom in the center of the top and bottom hexagons, and then 3 more atoms nestled in a layer halfway between the top and bottom.
Okay, a bit more complex geometry there.
It is. But the result is that same high packing density. Examples: cadmium, cobalt, titanium in its alpha form, zinc. These are HCP metals. And it's interesting, even though FCC and HCP have the same packing density and coordination number, that difference in the stacking sequence ABB versus ABC-ABC actually affects how they deform. They have different slip systems.
Ah, so even with the same density, the way they're stacked matters for properties like deformation. That's subtle. Okay, now you mentioned crystal systems earlier. How do they fit in with FCC, BCC, HEP? Are they like bigger categories?
Exactly. Think of the 7 crystal systems as the top-level classification based purely on the symmetry of the unit cell shape. It's all about the relationships between those lattice parameters, the edge lengths, ABC, and the angles between them, alpha, beta, gamma. The 7 systems are cubic, hexagonal, tetragonal, rhombohedral, sometimes called trigonal, orthorhombic, monoclinic, and triclinic. Each has specific rules about its axes and angles.
Okay, 7 basic shapes for the unit cells.
Pretty much. For example, the cubic system, which is the simplest, requires all 3 axes to be equal length, ABC, and all angles to be 90 degrees. Now, both FCC and BCC structures have unit cells that fit this cubic symmetry. So they both belong to the cubic crystal system, even though the atom arrangement inside the cube is different.
Ah, okay, so the system is the shape. The structure is the atom arrangement inside that shape.
You've got it. And HCP, with its hexagonal prism unit cell, naturally falls into the hexagonal crystal system, which has its own rules about axis lengths and angles. 2 equal axes at 120 degrees, a third different length axis perpendicular.
Makes sense. It's a hierarchy of classification. I also saw the term Miller indices. Sounds very specific, like coordinates.
Yeah, Miller indices, written as HKL, are a really neat notation system. They give us a precise way to name specific planes of atoms within the crystal lattice, or directions, which are written as UVW. They're derived from where a plane intercepts the unit cell axis. You take the reciprocals of those intercepts and reduce them to the smallest whole numbers.
Reciprocals. Okay. Sounds a bit mathematical.
It is, but it's incredibly useful. For example, a 100 plane is one that cuts the A axis at 1 unit length but runs parallel to the B and C axes. A 100 direction is simply the direction along the A axis. And for cubic crystals, which are nice and orthogonal, the Miller indices, a CHL of a plane, also happen to be the components of a vector that's perpendicular to that plane. Very handy for predicting things like cleavage or slip.
Okay, like a detailed map reference for planes and directions inside the crystal. Now, how does all this structure stuff connect to a basic property like density? It feels intuitive that tighter packing means heavier, right?
Absolutely intuitive and correct. We can actually calculate the theoretical density of a material pretty accurately if we know its crystal structure. The formula is density T equals N times A divided by Vc times Ne. Let me break that down.
Please do.
N is just the number of atoms that belong inside one unit cell. For FCC, it's 4. For BCC, it's 2. For HCP, it's 6. A is the atomic weight of the element. You get that from the periodic table. Vc is the volume of that unit cell, which we can figure out from the lattice parameters. And Ne is Avogadro's number, just a constant.
Okay, number of atoms per cell, weight per atom, volume per cell. Makes sense.
Exactly. So if you take chromium, for instance, we know it's BCC. You look up its atomic weight, figure out its unit cell volume from its known atomic radius, plug in N equals 2 for BCC. And the density you calculate is really, really close to the measured density. It shows how directly the atomic arrangement dictates that macroscopic property.
That's a great demonstration. And you mentioned general density trends between material types.
Yeah, there's a general trend. Metals tend to be densest, then ceramics, then polymers. So metals, ceramics, polymers. Generally speaking, it comes down to a few things. Metals often have those close packed structures, FCC, HCP, and heavier atoms. Ceramics often have less dense packing and include lighter elements like oxygen or nitrogen. And polymers, while they usually have quite low packing efficiency and are made of very light elements like carbon, hydrogen, oxygen.
So structure and atomic weight are the key drivers there. Okay, what about materials that can change their structure? I think it's called polymorphism.
Precisely. Polymorphism or allotropy, if it's an element, is this really cool ability some materials have to exist in more than one crystal structure. The structure they adopt often depends on temperature and pressure. Carbon is a classic example. You've got diamond incredibly hard, atoms locked in a strong tetrahedral network. Then you've got graphite atoms and hexagonal sheets that slide easily past each other, making it soft and a good lubricant.
Same carbon atoms, totally different properties.
Totally different. And then you have fullerenes, like buckyballs, and carbon nanotubes. All just different arrangements of carbon atoms leading to unique properties.
Amazing. Are there other important examples? Metals, maybe?
Oh, definitely. Titanium shifts from HDP alpha to BCC beta at high temperatures. But maybe the most crucial one, technologically speaking, is iron. Iron goes through several changes. Below 912 degrees C, it's alpha ferrite, which is BCC and ferromagnetic. Between 912 and 1394 degrees C, it flips to gamma austenite, which is FCC, denser and paramagnetic. Then above 1394 degrees up to melting, it goes back to BCC as delta ferrite.
Wow, it changes back and forth.
It does, and these transformations are fundamental to heat treating steel. The different structures have different abilities to dissolve carbon and different mechanical properties, so controlling these phase changes is how we make steels with specific strengths or hardness.
So controlling temperature lets you pick the crystal structure and thus the properties.
Very clever.
Like we've talked about this inherent order in crystals. Does that mean their properties are the same in all directions?
Good question. That brings us to anisotropy versus isotropy. Anisotropy means a material's properties depend on the direction you measure them in. This happens because the spacing between atoms isn't necessarily the same in all directions within the crystal lattice. So if you pull on a single crystal, its stiffness might be different depending on which crystallographic direction you pull along.
So a single perfect crystal is usually anisotropic. Direction matters.
Generally, yes. Take that BCC iron again. Its modulus of elasticity, its stiffness is quite different if you measure along the edge of the cube, 0, 0, 1 direction, versus along the body diagonal, 111 direction.
Okay, so single crystals have a grain to their properties. What about most materials we use, which aren't single crystals? They're usually made of lots of little crystals, right?
Exactly. Most materials are polycrystalline. They're aggregates of many tiny crystals or grains. Now, if these grains are all oriented randomly, pointing every which way,
then the directional properties average out.
You got it. The anisotropy of the individual grains cancels out on the macro scale, and the bulk material behaves isotropically. Properties are the same in all directions. However, sometimes during processing, the grains can become aligned in a preferred direction. We call this texture. If a material has texture, then even though it's polycrystalline, it can still exhibit anisotropic behavior overall, like wood grain, stronger along the grain.
That makes total sense. Random grains lead to isotropic behavior. Aligned grains can lead to anisotropy. Okay, how do these crystal structures actually form in the first place? Like when a metal cools from liquid to solid.
Right, solidification. It starts when the liquid cools enough for tiny stable clusters of atoms to form. These are called nuclei. They're the seeds of the crystals. These nuclei then start to grow as more atoms from the liquid latch onto them, arranging themselves in that characteristic crystal pattern.
So they grow outwards from these seeds.
Exactly. They keep growing until they bump into other growing crystals. And where they meet, that interface is called a grain boundary. Because those initial nuclei usually form randomly oriented, the final solid is made up of these interlocking grains, each with its own internal crystal orientation and separated by these grain boundaries.
And these boundaries, these seams between the grains, they matter too.
Oh, absolutely. Grain boundaries are really important. They're regions of mismatch in the crystal structure. They can act as barriers to dislocation movement, those defects that allow metals to deform, which generally makes materials stronger. Finer grains mean more boundaries, usually meaning higher strength. But they can also affect things like electrical conductivity, be sites where corrosion starts, or places where other phases might precipitate out.
So they have pros and cons depending on the application.
Pretty much. And in some cases, like turbine blades in jet engines operating under extreme stress and temperature, you actually want to eliminate grain boundaries altogether and use a single crystal to get specific anisotropic properties and avoid boundary-related failures.
Fascinating. Controlling grains and boundaries is key. Okay, finally, how do we actually see these structures? We can't just look, right? You mentioned X-ray diffraction. How on earth does that work?
Yeah, it's an amazing technique. X-ray diffraction, or XRD, is the workhorse for figuring out crystal structures and measuring the distances between atomic planes. It relies on the principle of diffraction. Diffraction happens when waves, like light waves or X-rays, encounter regularly spaced obstacles, and the spacing of those obstacles is similar to the wavelength of the waves.
Okay, waves hitting regularly spaced things.
And in a crystal, the atoms themselves form those regularly spaced obstacles. And X-rays happen to have wavelengths that are about the same size as the distances between atoms and solids. Perfect match.
So you shoot X-rays at a crystal, and then what?
Well, the X-rays interact with the electrons in the atoms and get scattered in all directions. Now imagine X-rays scattering off different parallel planes of atoms within the crystal. These scattered waves interfere with each other. If the waves emerging in a particular direction are in phase peaks, lining up with peaks, they reinforce each other. That's constructive interference, and we detect a strong signal.
And if they're out of phase?
They cancel each other out, destructive interference. We detect little or no signal. The condition for getting that strong constructive interference is given by Bragg's law.
Bragg's law again?
Yep, it's central here. It says nu equals 2 dhkl sin. Let's unpack it quickly. N is just an integer, usually 1, is the wavelength of the X-rays you're using. DKL is the distance between a specific set of parallel atomic planes, identified by those Miller indices HKL, and theta is the angle at which the X-ray beam hits those planes. So diffraction, that strong signal, only happens at specific angles where this equation holds true for a given set of planes, DHKL, and X-ray wavelength.
So the angle tells you the spacing between the planes.
Essentially, yes. We use an instrument called an X-ray diffractometer. It shines X-rays onto the sample, usually a powder, to get all crystal orientations, and it measures the intensity of scattered X-rays at different outgoing angles, usually plotted against 2, twice the Bragg angle. What you get is a diffraction pattern, a graph of intensity versus 2. It shows peaks, sharp spikes in intensity, at the specific 2 angles where Bragg's law was satisfied for different sets of HKL planes in the crystal.
So the positions of the peaks are the key.
Exactly. From the 2 position of each peak, you can calculate the d spacing for the set of planes that cause that peak. And for cubic crystals, there's a simple formula relating d, the lattice parameter A, and the Miller indices. DHKL equals A model plus AAL. By analyzing the set of d spacings you measure from the peak positions, and sometimes their relative intensities too, you can work backwards to figure out the crystal system, the lattice parameter, and the specific arrangement of atoms, whether it's FCC, BCC, HCP, or something else entirely. For instance, the pattern for alpha iron clearly shows peaks corresponding to its 110, 211 planes, confirming its BCC structure.
That is genuinely incredible, using scattered waves to map out atomic arrangements you could never see directly.
It really is a testament to understanding wave physics and applying it to probe the structure of matter.
Okay, well, as we wrap up this deep dive, let's try and crystallize the main point.
Later on.
We've seen that atoms arrange themselves in solids in either highly ordered, repeating crystalline structures or more jumbled amorphous ways. The basic repeating block of a crystal is the unit cell.
Right, and the way layers of atoms stack leads to common metal structures like FCC, BCC, and HCP, which differ in how tightly they're packed and how many neighbors each atom has their coordination number.
And these structures fit into 7 broader crystal systems based on the unit cell's geometry. We also learned about Miller indices for naming planes and directions within the crystal.
And critically, this atomic arrangement determines macroscopic properties like density. Plus, some materials can change their structure, that's polymorphism, depending on temperature or pressure, like iron or carbon.
We also touched on anisotropy properties depending on direction, typical in single crystals versus isotropy, where properties are uniform, often found in polycrystalline materials with random grain orientations.
And how these structures form during solidification, creating grains and grain boundaries, which themselves influence properties.
And finally, the amazing technique of X-ray diffraction using Bragg's law to decode these hidden atomic architectures.
Absolutely. And maybe the biggest takeaway is just how these arrangements, happening at a scale we can't even imagine, dictate the properties of everything we see and touch. Thinking about how understanding this lets us design materials, make steel stronger, copper conduct better, it really makes you wonder, doesn't it? What other hidden structures, maybe at the different scales, are quietly governing how things work all around us?
That's a fantastic thought to leave us with. And if this dive into the beautifully ordered world of crystals sparked your interest, please don't let it stop here. Please do like, share, and subscribe to the All Sorts podcast on YouTube. We've got a whole library of deep dives waiting for you there. And join the conversation. Connect with the All Sorts community on X, Instagram, and Threads. We'd love to hear your thoughts. Until the next deep dive, keep looking for those hidden wonders.